Hi, my name is Mackenzie Capo, and today I'm going to be going over a group of spectral problems that we were given. We were provided a group assignment number, a molecular formula, and a few spectral graphs, and asked to propose what molecule it was that we were looking at. So my group was group 7. We were given the molecular formula of C9H12. We were also asked to determine the degree of unsaturation within the formula, which by plugging in the numbers here, I have them color-coded, but you have 2n plus 2 minus h all divided by 2. We plug in the numbers of the carbon molecules and the hydrogen molecules, and we get a degree of unsaturation of 4. The degree of unsaturation tells us there's molecules here that are hydrogen deficient. So we're dealing with a molecule that either has double bonds, triple bonds, or a ring present, which provides us the hydrogen deficiency. We also have here the IR chart, which I have color-coded and interpreted here. And around like the 30-30 mark, we had an aromatic CH stretch. Around the purple here, the 2920, 2850 area, we have an sp3CH alkyl. And the blue here, we have around 1600, 1500, we have an aromatic C double bond C stretch. By looking at that graph, we can see that there is no strong peaks present around the 1700 area. So we know that there's no carbonyl group present in the molecule or no C double bond O. There's no broad peak also around the 3400, which reflects no OH group. So we're not dealing with an alcohol. This suggests that we're dealing with something that has an aromatic ring and an alkyl chain. By going back here, you can see here that we're missing those two elements, so we're able to determine that the molecule does not have either of those. Next up, we have the carbon-13 graph here, which we can interpretate here. I went ahead and color-coded it again as well. So we see around like the 140 mark, we have an aromatic C attached to the substituent. Around the 128, we have aromatic CH carbons. You can tell by the large peak here that there's multiple. We have the purple here, the 35, around the 35 area. We have a CH2 that's going to be near the aromatic ring. Around the 25 mark, the orange yellow, we have a CH2 or CH3 near the aliphatic chain. And we have around the 15 mark a terminal CH3 group. We can note here that with 5 distinct carbon environments, there is some symmetry present in the molecule. And last up, we have the hydrogen graph here. And by looking at this spectrum here, we can determine around like the 7.2 mark, we have a 5H multiplet, aromatic protons. Around 2.6, we have a 2H quartet, benzylic CH2 next to the aromatic ring. And 1.6-ish, we have a 2H multiplet, which represents a CH2, the middle of the chain. And at approximately 1, there's a 3H triplet, which is shows us that's the terminal CH3 group. So by putting this all together here with what we know now, we have a 5H aromatic. It fits with a monosubstituted benzene with an ethyl propyl-like side chain. So we were able to determine that there was a ring present, so there's some symmetry there. We have the ring, and then we also know that there's going to be 2 carbons and one final carbon at the end. So it was the C2H, C2H, C3H, all attached to the ring. So yes, so we know that there's 5 aromatic hydrogens. We have a monosubstituted benzene ring, which I have an example of at the end of the sentence there. We have the remaining hydrogens, the CH2, CH2, CH3 chain. We know that it's going to be directly attached to the ring based off of the benzylic CH2 at 2.6 parts per million. So finally, we have our proposed structure here, which is N-propylbenzene, which you can see we just put together the ring there, and then we put together the carbons that were in the chain and just attached them together, and that's what our molecule is going to look like. The benzene ring is present and other hydrogens are placed on a chain connected to the ring. All right, and thank you.